it's as we start our discussion of differential equations, it's important to keep this hierarchy that we discussed at the end of the previous session. We said that a closed form solution is really the best option, because okay, what do we mean by a closed form solution? When you have, let's say, a second order differential equation for y, okay, y is my unknown, it depends on t, and the second derivative of y with respect to t is given as some function of y dy by dt and t. A closed form, and of course presumably it contains some parameters too, some alpha, beta and so on. These are all constants that appear in the problem. You could think of them as parameters. For instance, if you have a vibration equation, then this could be the mass or the spring constant and so on. Those are all parameters. And a closed form solution basically gives you y as a function of t, alpha, beta and so on. Okay, that's what you mean by a closed form solution. You write down an expression, y is equal to alpha sine t, whatever, some form of it, right? That is a closed form solution. Now, that's the best because it tells you explicitly how y depends on not only time or t, the independent variable, but also on the parameters themselves. So if you go back to our discussion about this rod with aluminum and copper and things like that, then presumably all the stuff about aluminum or copper is encoded in alpha and beta. So you know exactly how the solution will change if you change those physical parameters. So that's why that's the most preferred. The next one was what I call quadrature. I'm going to modify that a little bit. I'm going to say quadrature or series, and by this I mean that there is a way to calculate this. You have an expression, presumably an integral or a complete infinite series, and you can calculate it to any desired accuracy. So you can use a numerical technique to evaluate the integral, or you can get, let's say, 10 terms or 5 terms or whatever of the series. That's all you need, right? And so these two can come together. That's the next degree of sophistication. You know the dependence, okay, y is equal to some integral of some function times dt, and presumably it has all the coefficients are here inside this hashtag symbol. So you can evaluate the integral and then you can get solution. Series is likewise, you have y equals summation over I, some t, some gi of t times some coefficient, and presumably the coefficient contains, these are constants that contain alpha, beta and so on. Gi of t are some series of functions. For example, g1 could be just t, g2 could be t square and so on. Then it's a power series. Gi could be cos it, sin it, then it's a Fourier series and so on. So in general you have an infinite number of these terms going from 0 to infinity, and depending on what degree of accuracy you want, you can evaluate as many terms as necessary. So this is the next degree of sophistication, right? Next degree of, well, less hopeful than this, but certainly not too bad. And the third one is, of course, where we do qualitative solutions. For instance, we ask what happens to the limit t goes to infinity. That's one question you can ask, and that will tell you something about the ODE itself and of the solution to the ODE itself, and what it will do as t goes very large, very small. These are things you can do. That's a qualitative solution. For that we need some graphical pictures. We'll develop them today and in the next session. And finally we will have to resort, if none of these work, you'll have to resort to a numerical scheme. Okay, and this hierarchy we should keep in mind. Why should we keep it in mind? Well, this is the hierarchy I'm going to use with the first order system, with a sequence of first order systems, to show you how you can go from seemingly simple problems. Okay, first order systems for which you can get closed form solutions are all linear. There are others, but okay, linear systems you can always get a closed form solution, and linear systems are for first order, they're fairly trivial. They're not really very useful. They do occur once in a while, but they're not the most interesting ODEs. And then we'll go to this, and then maybe for first order we might not see too many examples of this, but then we'll move to this very quickly, and we'll spend some time on this. So we'll try to develop this idea of what is called a phase space. That's what we mean when we say graphical picture. So that's an intrinsic way of thinking about ODEs and about their solutions, and trying to use geometry as opposed to algebra to answer some of these questions. So instead of sitting down doing integrals, instead of using calculus and so on, we start using geometry. What happens to this curve, what happens to that, and things like that. And numerical scheme, again, for first order system it's fairly straightforward. You can just use time stepping an Euler scheme. So I won't mention it. We'll talk about numerical schemes when we come to second order systems. Okay, so same scheme will follow, sort of for an illustrative point of view. We'll use first order systems here with the same scheme, and once we get the basic hang of it, especially with this, how to construct phase space, what these pictures look like and so on, then when we come to second order systems, you will see that this is more systematic, and it's a very clever way of dealing with any possible differential equation that you can come up with. Okay, so that's our plan. Okay, so let me start with let's start with the first order system. Okay, the general first order ODE is going to look something like this. Okay, where G is in general a nonlinear function. I think we mentioned this in the first session. It could be any arbitrary nonlinear function, and the differential equation is nonlinear if G's dependence on y is nonlinear. So you could have a linear equation where G depends nonlinearly on t. So G could be like exponential to the t or t to the power 3 by 2 or whatever, but as long as its dependence on y is not nonlinear, you will not call it a nonlinear equation. So it's only nonlinear if G, the y dependence of G is nonlinear. Okay, it's something to keep in mind. So for instance, to see what nonlinearity is, let's see what linearity is, so that you know if it's not linear, it's nonlinear. So a linear equation is basically something that has G of yt of this form. It looks like a of t times y plus b of t. Okay, that's the general linear equation. Okay, a and b are, again, notice they're arbitrary functions. I'm not saying a of t is proportional to t or b of t is proportional to t. They're arbitrary functions. They could be nonlinear functions of t, but it's still a linear ODE. Okay, it's important to recognize this. I'm sure you've seen this before, but it's important to keep this in mind. Good. So when you have a general linear equation, there are subclasses that you can write down. We can list them out. Maybe it's worthwhile to do that. Let's do that. So if b of t is 0, then it's called a homogeneous equation. If b of t is non-zero, it's called a non-homogeneous equation. Okay, that's kind of obvious. If b is equal to 0 and a of t, or b of t is constant, it can even be a constant, but if a of t is equal to constant, so a of t doesn't depend on t explicitly, then it's what's called an autonomous equation. Okay, so these are three terms that you will come across that we'll use repeatedly, and it's important to recognize what they are. Okay, so that's why I've just put it down. I'm sure you know this, but you've seen this at least in some form before. Good. Okay, so if let's take the simplest homogeneous case. Okay, simplest homogeneous ODE is first order is just this dy by dt is a of t non-autonomous. A can depend on t arbitrarily, and this is, well, straightforward enough to solve. You just do cross multiply, you get 1 by y dy is a of t dt. You integrate it, so you'll get ln y is integral a of t dt plus some constant. I'm going to call that constant c. We call it capital A. Okay, and then I will take an exponential. So I will get y is exponential of this whole thing if I take out the log on this side. So then it will be exponential of this times exponential of this. I'm going to call exponential of a as some other constant b. So this will just be b exponential of integral a of small a of t dt. Okay, that's easy enough. So that's a closed form solution. That's the one we started off with. Okay, it's easy enough to get. Okay, let's see an example, maybe a couple of examples, just to make sure that we're all on the same page. Again, these examples are not the most useful because you will seldom see first order equations of this kind in physical situations, but still it's important to be able to do this so that it builds not only intuition but also builds algebraic skill in doing integrals and so on. So for instance, I'll give you a couple of trivial examples, not just from the point of view of okay, you can use this formula and get an answer, but from the point of view of illustrating something important about the solution. Okay, we'll see how that works. So let's start, for instance, with dy by dt plus, let's make up something, plus let's say sin t times y is equal to 0. Okay, that's a first order linear differential equation. Yeah, first order linear. If you had a y square, then it's non-linear, but here it has only y, even though you have sin t here. And so you can do the same thing, cross multiply, integrate, you get 1 by y dy integral minus sin t dt. And this is a indefinite integral, of course. I have not put any limits, those will come later. And this is just cos t plus a using the same notation as there. This is ln y, that is what this guy is. So when I exponentiate, I'm going to get y equals b exponential of cos t. Okay, it's easy enough to do. And now I can replace it with anything. I put some function, you will just cross multiply and integrate, and that's all good. Okay. Now remember at the start, we said there are three questions that people are usually interested in, different hierarchy. First is what do we mean by a solution, and the second is when does such a solution exist, and the third one is, of course, if you know the solution exists, you go ahead and find it. And I also mentioned that I will talk briefly about the first 2 points, and we'll spend the rest of this whatever 10 lectures on the third point, because that's the one that we are most interested in. It will turn out, we will see the criteria in a minute, that for all reasonably well behaved systems, physical systems, existence is almost always guaranteed. Okay, it's always going to have some solution, unless you come up with something really bizarre and it's not going to make any sense. So the question of existence we will address and be done with, but the question of what we mean by a solution is something that is a little bit tricky, it's a little bit deep, and that's what I'll talk about right now. Okay, so first, before we do that, let's say this is example 1. Let me make another example. It's a completely synthetic example, I'm making it up, but it will serve to illustrate a point. So for instance, let me take the same equation and I'll replace this with p of t. Okay, same thing. Now I'm going to say p of t is let's say sin t if t is greater than 0, and it's 0 if t is less than or equal to 0. Okay, so I have p of t is the same as this. So if for positive t, t is the independent variable. For positive t, this equation is the same as this. For negative t, it's dy by dt is equal to 0. Okay, so now what happens? What is the solution to this? The reason I'm putting this sort of cooked up example is to show you something about the nature of the solution. That's the first question, right? What do we mean by a solution? Now there is the usual tendency to assume that, okay, you know, you have a solution that looks like this, of this form, and okay, presumably it's differentiable and it's multiply differentiable, so you can keep taking derivatives as far as you like, but that's not necessarily always true, and that's something you want to keep in mind. In general, the solution is only as differentiable as the order of the differential equation. So for instance, this solution, you can guarantee that it is differentiable once, because the derivative appears here and it's well defined, and there is really a priori no guarantee that there is a second derivative or the second derivative is continuous. Okay, this is a good case in point, that's why I have made this up. So if t is greater than 0, you have the same solution, so then y will be just b exponential of cos t and if t is less than or equal to 0, then p of t is 0, dy by dt is 0, y is constant, some other constant, let us say c. Okay. So, this shows us one example where the coefficient in the equation, this is a linear equation, simplest linear first order ODE that you can think of. The coefficient has a discontinuity, presumably can have a discontinuity over here, although in this case it does not. I could have made this cos t, in which case it will have a discontinuity. And the solution as a result has to be broken up into two parts. The first part has this expression, the second part has this expression. Now, there is no reason a priori why the solution has to be continuous as t goes from minus infinity to plus infinity, as t crosses the origin basically. Okay. So, that is again something you want to keep in mind. So, there is no need, no a priori need for solution to be continuous. Okay. In which case you will have two constants b and c, both are undetermined as of now, and so you are going to need some additional piece of information, some additional physical content, some additional law and things like that to actually resolve this problem. Okay. So, a priori there is no need for the solution to be continuous. If you insist, if continuity is needed, like if the physical problem, if the variable that you are putting into the differential equation is such that it cannot physically admit a discontinuity, then you have to enforce continuity on the solution, and then what you will do for that is you will set as t goes to 0, this solution is equal to this solution, so it is continuous. And if you do that, the left hand side solution, the less than 0 is c, the right hand side solution is b exponential of cos 0 is 1, so it is exponential of 1, that is b times e. And so, then you will get a relation between c and b, and you will get one constant that is unknown. Okay. So, in general you could have a situation where something like this comes up, and in that case you have to be a little careful before you jump and assume that the solution is everywhere differentiable, continuous and so on. Okay. That is not necessarily true. Okay. So, this is a very good example. P of t, in this case, let us take this case, P of t is continuous, but its derivative has a jump. Okay. Here it is cosine t, here it is 0, it is defined to be 0. So, the dy by dt has this, well, it is continuous, but then the d square y by dt square will have a jump. Okay. And so, you have to be careful whenever a situation like this comes up, that is the point. Okay. Good. So, in general you cannot assume that the solution is continuous differentiable how many ever times you want. If the coefficients are such that they are functions of t and they are continuous and multiply differentiable functions of t, then in all likelihood that the answer, the final solution will also be continuous and differentiable, but that is not guaranteed. Okay. Just something to keep in mind. Good. So, we have illustrated this idea of function does not necessarily have to be does not necessarily have to have multiple derivatives defined. Let us illustrate another idea. Let me take another example. Let me say another first order differential equation, dy by dt plus y, let us say is 2 cos t. Okay. This is a non-homogeneous equation, right hand side is non-homogeneous, and you have a term that is not multiplying y presumably, so it is a non-homogeneous equation. And what is the solution to this equation? Well, let me give you one solution. So, so now we are going to answer the question, what do we mean by a solution again? So, let me say, let us say y equals sin t plus cos t. Let us see if this works. If I have sin t plus cos t, dy by dt is cos t minus sin t, dy by dt plus y will give you 2 cos t. Okay. This works. So, this is the solution to this. Is that what we mean by a solution? That is, well, yeah, I mean this is a solution, so why not, right? What about this? If you take this to dy by dt, let's try it out. This will also be a solution. Dy by dt will give you cos t minus sin t minus 3 e power minus t. If I add y to it, I am going to add this again. So, it will be sin t plus cos t plus 3 e power minus t, and the sum of these two is 2 cos t. It's the same as this. So, this is also a solution. Okay, and now we are sort of in this strange situation. We have a first order ODE. We have all learnt, okay, first order ODE has one solution presumably, whatever that means. But now I have given you two solutions and both work. Turns out, if you have seen this before, you probably have. If I change this to 10 or 100 or any constant, any irrational number, does not matter, I can make it pi, it will still be a solution of this equation. Okay. So, the general solution, as it turns out, again this is probably something you can solve right now, but just for for illustrative purposes, I am going to go through this systematically. So, a general expression of this form will be a solution to this equation. Okay. And so, this idea of what is a unique solution is something that we have to address a little bit carefully. Clearly, there is seemingly no uniqueness here or here, because you can get infinite solutions by changing c over whatever value or any real number. So, the question what we mean by a solution means that the system, the actual problem should actually have two parts. One part is a differential equation, and the second part is what we will call an auxiliary condition. So, it is extremely rare that in a physical problem you will just end up with this and you will solve it. It is almost certainly never going to happen. What will happen is you will have a full problem specified like this. So, you will have a differential equation presumably like that, and you will have an auxiliary condition. The auxiliary condition could be in the form of an initial condition or a boundary condition. We will see what these terms mean. In first order systems, fairly trivial because you have only one derivative, but in higher order systems they will start making more sense, and they will fundamentally alter the nature of the solution. Okay. So, a full problem consists of a differential equation plus an auxiliary condition, plus auxiliary conditions, plural. You could have many, you could need many. Okay, we will see why you would need many. Okay, that is what you mean by a full problem. And when we say a solution, we mean a solution to this full problem. That is what we mean. When we say solution of differential equation, we are not talking about solution of just this, a general solution. Usually we are not, because we are interested in applications in physical problems. And so, when we say solution, we are talking about a solution to this full problem. Okay, very important. Please keep it in mind. If you don't specify the auxiliary condition, we are actually talking about families of solutions like this. For arbitrary c, there are infinite of them. This gives you a big family. And for by putting different values of c, c is equal to 0 will give you this, c is equal to 3 will give you this, and so on. Okay. So, talking about a solution, we will pick one particular value of c or analogous in the solution. Okay, that is something to recognize. Good. So, that is what we mean when we say a solution to the system or solution to the problem, or even solution to the differential equation, even though that is misleading. Okay, good. Now, the second question we have to ask, and second question will start off perhaps from here. Notice I have said auxiliary conditions, I put that little plural s sneakily at the end, but that is really important. Okay. So, the first question, what is the solution, is sort of answered. Second question is when will a solution exist? Okay, for that we need to make sure that the problem is complete, is completely specified. Okay. So, for this we need to first ensure problem is completely specified. Okay, what do we mean by that? Well, let's go back to the differential equation I wrote down before. Dy by dt plus y, what was it, 2 cos t. Okay, I said there is an auxiliary condition that you will need. Remember, this had one constant. The general solution had sin t look like this, and it had one constant, and you can fix that constant by specifying y at some point in the domain, right? Domain is the first thing you need. So what do we mean by that? Domain is what values of t. So does it go from 0 to infinity, minus infinity to 0, 0 to 2 pi, whatever, right? That's the domain. And the second one is by specifying, for this equation, specify y at some point on domain. Okay. So, if you have the differential equation, then you put the domain and then you specify y, at least for this first order equation, you specify y at some point on the domain, then you are done. Okay. Then you will have a completely specified, well defined system for which you can get a solution. But this is okay, this is for the first order case, and notice also you need to specify y at some point. We maybe say a couple of things about that. So, you say y at, let's say, t naught equals y naught. Okay. This could be, t naught could be the beginning point of the domain. For instance, this could be your domain going from t naught all the way to infinity. Notice I put the square bracket, so t naught is included as part of the domain. It's closed on the left end, this set, and the right end it's open. So I've got this parenthesis there. And if I specify y at the initial point, it's sort of like an initial starting point for the solution, right? Okay, so you could call this an initial value problem. Okay, for, like I said, for first order ODEs, the distinction becomes fairly trivial between initial and boundary value problems, but okay, at some point I could specify it at some other point within this domain also, and I'll be fine. All I need is one equation to solve. So if I give t, whatever, t greater than t naught, let's say 3 t naught, 4 t naught, whatever, then I will get the value of y. I will have a full equation I can solve for c and then get the actual solution that obeys this condition. Okay, so the full system will be specified, and that will be the solution that solves the entire system. Okay, good. So this is for a first order system. Now what do we do for a second order system? Well, the problem is the following, or a higher order system for the matter, third order, fourth order, whatever, right? The problem is the following. You've probably heard that for a second order system you have to specify the value of y and the first derivative. That's one possibility, right? Yeah, you could do it now. You will start realizing things start becoming a little bit more complex. Do you specify all of them at one point? If you had a domain, let's say, that looked like this, do you specify the value and the derivative at t naught? Do you specify value at t naught, derivative at t1? Do you specify, vice versa? Do you just specify derivatives at both points? For a second order system, what do you do? Right? So things become a little bit more complex. Now you can think about all of these in a more generalized framework, and that's what we will derive now. But the basic idea is the following: why do you need to specify the position? Okay, that's a question you can ask, right? Why do you have to specify y to get c? Okay, it looks like getting one equation for solving for one unknown. That's basically what you're doing. But why do you have to specify this? Why can't you specify like this first derivative of y or the second derivative of y, something like that, right? To answer that, let's look at a more general, a simpler example. Let's say I take this. This is the first order. Let's take the first order equivalent of that. Okay, this. right hand side is 0, this is the homogeneous equivalent of this. I have removed the non-homogeneous term, I have only this. So, okay, the solution is fine. This is YAC power minus t. You just cross multiply and integrate, you will get this. And you need one condition. Okay. If you think about this equation, sort of analogous reasoning goes through for this as well. It's a little bit more complicated because it's non-autonomous, but we'll stick to the autonomous case now to make things clear, and then we'll make things more complex later on. If you think about this solution, in principle, from a purely algebraic point of view, this is a very differentiable function, so I can take how many derivatives I want. Each will just give me e power minus t with a negative sign in front. So presumably I can specify, okay, maybe I can specify d3y by dt cube is c with minus e power minus t. So you could ask, okay, why can't I specify the third derivative of y and then use that at some point, maybe t naught, and then use that to calculate c and then put that c back in here. Well, algebraically you can, but from a physical point of view, it makes absolutely no sense to do this. Okay, and the reason is, you can write this equation as dy by dt equals minus y, and this is the framework that we should get used to thinking about differential equations, ODEs of this form. If you use this, if you just recast this, put y to the right hand side, it basically tells you that the derivative is determined by the function. Okay, what you're doing here is you're determining the function from its higher derivatives, which makes no sense from a physical point of view. Derivative is determined by the function. This is like LHS equals RHS, unknown and known. Think about it like that. Okay, even though y is not known, think about it on that framework. Okay, so whatever you have here is going in and determining the derivative. Okay, so when we get to a construct called the phase space construction, you will see that the only thing that matters finally is the actual solution curve y of t. Okay, after you account for the c, the only thing that really matters is y of t. That determines everything, whether you can have higher derivatives, whether you can't have higher derivatives, what their values are, and so on. Okay, so that's the fundamental property of the system. That's the physical variable you started off with. You didn't start off with the derivatives. The physical variable you started off with is y. So y contains all the information. Now we'll make a generalized version of this when things will become a little bit more clearer. So let's say I have, for instance, again we're still within this question, how do you fully specify the system? Let's take, for example, a third order derivative differential equation, d square d cube y by dt cube is or plus p of t. Let's take a general linear third order system. Homogeneous system. This is linear because, okay, all the derivatives appear. There are no, for example, there is no term that has dy by dt the whole square or y to the power 3 or whatever. They are all linear in each of those derivatives. So it's a linear third order system, third order because highest derivative here. But it's not autonomous because p, q, and r can in general depend on t. Okay, so that's something you want to just keep in mind. This is r, by the way. Let's write it like that. Okay. Now, the same discussion of requiring these auxiliary conditions will carry on to this, but now what type of auxiliary conditions do you have to specify? Okay, what type of conditions can you specify? To do that, to see that, let's change variables. Okay, so I'm going to call y as y0. I'm just changing the labeling. Okay, I'm going to call y1 dy by dt as y1, and I'm going to call d square y by dt square as y2. Okay, I'm just going to rename stuff and I'm going to rewrite this. So since y is y0, dy by dt is just dy0 by dt is y1, that is just rewriting this in terms of y0. Similarly, d square y by dt square is d by dt of dy by dt, but dy by dt is y1. So, y2 is dy1 by dt is y2. So, I have used this equation, I have used this. Now, I will go back to the original equation. D cube y by dt cube is d by dt of the second derivative is y2. So, this will be d by dt of y2. So, dy2 by dt, and I will push this entire fellow to the right hand side. I will replace this with this, this with this, and this with this. Okay, and just write it down. I get minus p of t y2 minus q of t y1 minus r of t y0. Okay. So, I have started from a third order equation. I have got 3 first order equations. Okay, only first order. This is the definition, but it does not matter. As long as I have made the substitution, this system is equivalent to this system. Okay. So, I can write this system. Okay, this is a linear system. I have y0, y1, y2, y0, etc. The differential equation was linear, so this is the linear system. So, I can write this if I write y bar as, you all finished the part on linear algebra. So, here is some linear algebra for you. If I write this as a column vector, this is transpose, then I can write this entire system as d by dt of y bar is A times y bar. A is a matrix, 3 by 3 matrix. Okay. Any third order linear differential equation can be written like this. Now, you can imagine the same procedure if I had a 7th order differential equation. I will redefine variables like this y0, y1, y2, y3, y4, y5, y6 up to the 6th derivative, and then I will get a column vector that has 7 entries, right. So, 7th order 7 entries, third order 3 entries, and it will be equal to some 7 by 7 matrix times the same vector. First order equation, linear first order equation. Okay, linear homogeneous. So, this should tell us 2 things. First, it should tell us that okay, studying linear homogeneous equations, first order equations is useful, because a higher order equation you can cast it in this form. So, presumably something that you learn from a first order linear homogeneous equation you can directly apply here. And notice it is not yet autonomous, because p, q and r depend on t. Maybe I will just write down this A explicitly. So, I have A over there will be y0 will be 0 1 0 0 0 1 because of y2, and then this guy will give me, so dy2 3 minus r minus q minus p. Okay. So, this is what A is. A is a function integral of t. Okay. Good. Now, you can start seeing some of this complexity as you go to higher order equations. Firstly, okay, we have got a first order system and this is a coefficient matrix A. How do we completely specify the system? Again, we are still continuing with that question of how is the system fully specified. How do we do this? Well, for a first order system, we have seen that you specify the value of y at some point in the domain, let us say t naught. So, let us say domain is t naught to t1. Okay, that is my domain. Now, if you just take whatever we have seen for the first order case and apply it to this system of first order fellows, then that means for each of these I have to specify y0, y1, y2 at some point presumably within this domain. Okay, so, the simplest thing will be specify y0 of t naught, y1 of t naught, y2 of t naught. Okay, because you have 3 equations, you have 3 of these fellows y0, y1, y2. The differential equation is in y0, y1, y2, 3 of them, they are all coupled. just like when you had dy by dt is equal to something times y, and then the left hand side specified at some point t naught. You do the same thing here. Okay, now you only do it for 3 of them. If you go back and see what the substitutions meant, that means specifying either y at t naught, which is what this is, y1, which is the derivative, which is dy by dt at t naught, and d square y by dt square at t naught. So, for a third order equation, one way to completely specify the system is to specify these 3 at the same point t naught. Okay? And if you do that, then that means specifying the function, the first derivative, second derivative at a particular point in the domain. If you do that, then presumably the constants that come out of integrating this, okay, I don't know if you can integrate this because p, q and r are arbitrary right now, but the constants that will come out will be resolved uniquely, and then you will have a final unique solution that has some y as a function of t. Okay, so if you specify these 3 derivatives at one point, that works. Okay. This is what is called an initial value problem. And in this part of the course, when discussing differential equation, we are going to be mainly looking at initial value problems. So, you specify all 3 of this system at a particular point t naught, and the t naught is the beginning point of the domain, let us say. I mean, you could translate it, you could change things, specify it at some other point, but okay, from a physical point of view, t naught can be the start of the domain because it makes things a little bit more intuitive for us. Okay. But you now realize there are other possibilities, okay, which were not there in the first order system. What are these other possibilities? Well, I could specify y0, y1 and y2 at different points, different t's. So, I could specify y0, so this is one option. Second option, I could specify y0 at t0, y1 at some other point, t0 tilde, or let me call it use t1, let me use y1 at t0 tilde, some other point, and y2 at t0 hat, 3 different values. Okay. That is one possibility, certainly you can do that, right, but there is nothing stopping you from doing that. So, the first order case you have only one condition, so it does not really matter. There is another possibility which really did not come up in the first order system, which is that I can specify, I need 3 conditions finally. Remember, this is synthetic, this is the original. So, the synthetic version seemingly, because of this analogy with first order, looks, needs something like this or like this. But remember, it's a version, the original version is this. So, what I can do instead is I can specify y0 at t0, I can specify y0 at t1, and then specify maybe y1 at t0. I can do that. Okay. So, I specify the same variable at 2 different points. One is at the beginning of the domain, one is at the end of the domain. This is called a boundary value problem. So, initial value problem is IVP, boundary value problem is okay BVP. Okay. Now, you could come back and take some combination of this, and then you could say, okay, I will specify these 2, I will put this at some other point, which is also fine, or I will specify y1 at t0, y1 at t1 and y0 at some other point, or I could think of y2 at t0, y2 at t1 and y1 at some other point, but you need 3 conditions. So, all the other variants which do not specify or which specify things at multiple points like this, they are all called mixed boundary value problems or mixed initial boundary value problems. Okay. So, this distinction is important, and you notice it starts becoming important only as you go to order 2 and above, because of these multiple possibilities. In order 1, it is fairly trivial, there is no distinction between these 2. So, in what we are going to do, like I said, we are mainly going to focus on IVPs, not so much on BVPs. Maybe I will mention a few things about BVPs because they are a little bit more cumbersome. The pictures will develop, the ideas that we'll talk about, the qualitative stuff, even the numerical schemes will all be mainly for IVPs, because they're sort of simpler. They give you a good hold of the situation. Boundary value problems can be highly non-trivial. You have to be careful when you choose a solution, and oftentimes existence becomes an issue. Okay. Good. One last comment about this is that so if you specify an initial value problem or a boundary value problem or a mixed version that has enough conditions, then you have fully specified the problem. Okay, that's coming back to answer the original question. Good. So one more sort of thing to keep in mind is usually an initial value problem comes up when t is like a time variable. You can understand why, right? When it's like Newton's laws, you give the position and the velocity at t equals 0, and then you shoot the projectile and it's going, and then whether it falls on the person's head or not is probably the end result. So usually t is time. In the case of boundary value problems, since you specify things at two different t's, usually t is like a length. Again, this is just some physical insight. It's not a hard and fast rule. You could have situations where the opposite happens, but usually this is what you would see. Okay, and standard examples of this, for instance, boundary value problem could be like a beam simply supported at two ends. The boundary conditions are basically these. You specify whether the slope is 0, whether the momentum 0, the moment is 0, whether the force is 0, whatever, deflection is 0. Those are all boundary conditions. For instance, like in a cantilever beam that's suspended at one end, stuck at the other end, you will have conditions that t equals 0, t equals L, length of the cantilever, right? So that's a typical example of this. Okay, so that's one thing to recognize. Good. So now we know how to specify a system. System means for us, for now, an initial value problem or a boundary value problem, mainly an initial value problem. And good. So we've realized that you have to talk about a solution, you need an initial value problem. You don't need just a differential equation, you need an initial value problem. So now the next logical question that we come to is, if somebody came, you're walking on the street, and then like you do every day, there is someone who comes up to you and says, hey, I have an initial value problem, can you solve it for me? Okay, it happens all the time. So the next question is, when does a solution exist? Okay, and like I said at the start, like I've said a couple of times already, this is a question that we'll really not be worried about so much, because the physical problems that we're interested in, most of the times they will obey the conditions for existence and uniqueness. But given an initial value problem, and I'll write it down in the form that we wrote before. So we had a linear form, remember we had dy by dt, we just derived that for the third order system. A was some arbitrary function of t, but it's still linear. The general version of this is when you have something that looks like this. Okay, f is also column vector because y is a column vector, so presumably f is a column vector, and it's a function of the y's, individual y's. Could be a nonlinear function in general, in which case it will be a nonlinear system, but it's a function of the y's. For the special case of a linear system that we worked out for the third order equation, you had f bar but t was just a times y bar, right? That's what this is. But general nonlinear case is what we'll use. Okay. So for this general nonlinear case, if you go back and ask the question, when does the solution exist? Okay, now we've realized that this initial value problem, we'll specify y bar at t naught is some y naught bar. So I'll specify that entire column vector at some initial t. I've given the domain also, t naught comma t1. So at some point, let's say the initial point, for making things easy for ourselves, the initial point I specify the entire column vector as being some constant vector, y0 bar. This has entries, whatever, 1, 2, 3, 4, whatever, some numbers. Okay, depending on the order of the system, depending on the dimensionality, whatever. Okay. Good. So when does this system? So this now constitutes an initial value problem. Okay, this system, differential equation, domain, and the initial condition constitutes an initial value problem. And there is something called Picard's theorem, which tells us when a solution will exist and when it will be unique. So, for example, I mean, you do all the hard work, you find a solution, but you don't know a priori if the solution is unique. Is there some other solution that obeys this problem, right? Picard's theorem guarantees that there isn't. So, what does it say? Well, it's probably the only time I'll write down a theorem, even though this is a maths course. It's like I said, the emphasis is on getting answers than on just pontificating. But anyway, I should stop saying stuff like that. Picard's theorem says that if f bar of y bar comma t is such that f is continuous, in the vicinity of t0 comma y0 bar. Notice y0 bar is a column vector, t0 comma y0 bar is think of it as a column vector with one additional entry, which is t0 here. Okay, so in the vicinity of this point with coordinates t0 comma all the other y0s appended to it, if it's first continuous and if dou f by dou yi, these are components of y, so yi are components of y bar. Okay. So, if dou f by dou yi, and remember f bar is also a vector, I forgot to put that, f bar is also a vector, so it also has components 1, 2, 3, 4, 5, how many ever. If each of those components, if the derivatives with respect to yi and the derivatives with respect to t exist, in a neighborhood around t0 comma y0 bar. So, you take this point in presumably n plus 1 dimensional space. Okay, it does not matter for now, this is just a row vector, let us say, with all these entries. If just in the vicinity, if you have t just near t naught on either side and all the y's just around that initial point y0 bar, okay, and in that zone, that region, what we call the neighborhood, if this derivative, sequence of derivatives, remember there are multiple components to f bar and you have to take derivatives with respect to each of the i's, the components of y, and the derivatives of each of those f bars with respect to t, if they exist, the partial derivatives, if they exist, then there exists a solution to this initial value problem. Let me call this star, to initial value problem star, and the solution is unique. But in the same neighborhood. Okay, same neighborhood as this. So, wherever in that little zone, wherever these derivatives exist and f is continuous, in that zone there is a solution, solution is unique. Okay, the moment this gets violated or this gets violated, then you are in trouble. Okay, so this is what Picard's theorem basically says. It guarantees that the solution exists and is unique in this sort of neighborhood where the right hand side of the function is well behaved. Okay, let us just use that phrase, because in most physical situations, as you will see, the right hand side obeys those constraints. Now, this theorem is a little bit subtle. Obviously, I have gone over all of this subtleness or subtlety. I've gone over all of the subtlety to just get to the point, just make a point, but it is a fairly involved idea, and it draws on several ideas from what we mean by a continuous function, what do we mean by continuity, what do we mean by differentiability, and so on. But like I said, for all practical purposes, this is what we will need. Okay, good. So we know when a solution exists. It exists when f obeys this, or the right hand side of the system obeys this, in the vicinity of this. So you notice again, even the existence result also takes into account the initial conditions. Okay, this is for an initial value problem, of course. Like I said, the boundary value problem can be a little bit more cumbersome and complex, just to show that they have a solution is unique. But for an initial value problem, the initial conditions are part of the formulation. So there is no question of just solving a differential equation per se. It's a very naive question. You can do it, okay, somebody gives you a differential equation, you can try to integrate it and get a solution, but usually in physical situations, you are always talking about an initial value problem. Okay, so that's, I hope I've hammered that point home. Okay, so now that we've got some of these questions out of the way, let's start in earnest with this 1D system, and we'll sort of breezily course through 1D systems because fairly simple. And like I said, the reason we want to do this 1D system is to explain that original hierarchy from closed form solution to qualitative techniques. Okay, and so we'll use the 1D solution briefly. We'll use the 1D solution to construct phase space and things like that. Okay. Okay, so let's take general 1D system again. We have this, some nonlinear function, and then I put a condition. Y naught is some constant. Okay, this is an initial condition, and the domain is t belongs to, let's say, t0 comma infinity. Okay, this is infinity. In general, you cannot solve this, of course. I mean, it's not necessarily that you're able to solve this depending on the type of function that you have on the right hand side. But okay, if you go back to the linear case, which is something that is of interest, this is linear. Again, non-homogeneous because there is B, non-autonomous because there is B and A, both are functions of t. And you can solve this equation fairly easily. People have probably seen how to do it. You bring this guy to the left hand side, dy by dt minus a of t times y is b of t. And usually, people will use something called an integrating factor. It's a clever trick that you've probably seen before. The only thing you have to do is you have to take line is not straight. Whatever. So you have dy by dt minus a of t times y equals b of t. You multiply both sides by e to the power of minus integral dt. Actually, let me do one thing. Let me change this notation. Let me just rewrite this. I just don't want to carry this negative sign around everywhere. Let's just look at the first order case as being like this: dy by dt plus p of ty. Okay, just analogous. Q is the same as b, p is minus a. Okay, so now you just multiply this by exponential of integral p of t dt. So you will get e to the power of integral p dt dy by dt plus p e power integral p dt, y is q e power integral p dt, and you will immediately recognize that this is the same as d by dt of e power integral p dt times y, because you have product rule. You open it up, you will get, open this up, you will get this, and this is just q e power integral p dt. Again, this is something that you've probably seen, gate syllabus, whatever. and this thing that you multiply with is usually called the integrating factor. I am putting it out for two reasons. One is for completeness, of course, just to make sure that I have told you what this is. But the second more important reason is that there is an alternative way of looking at this, and that alternative way is a little bit more insightful because it tells us something very fundamental about linear systems, and it also gives us some recipe for tackling higher order linear systems as it works out. And we will derive that just based on this final result. So, let us just go through with this. Let me finish this off. Integrating factor, and so then this right hand side is purely a function of t, because p is a function of t, whatever, q is also a function of t. So, I can just take this the other side, integrate, get e power integral p dt times y is equal to integral q of t e power integral p dt dt plus a constant, some constant as you integrate, integration constant. This is a indefinite integral. So, then I can write down y, maybe I will write it down here. I can write down the solution over here. The solution will just be y equals e power minus integral p dt times c plus integral q of t e power integral p dt dt. Okay, so you have two terms, and this is what it looks like. Yeah, so people have seen the solution, I hope. Integrating factor stuff. Okay, now the reason, like I said, the alternative way of looking at this entire enterprise is as follows. I can open this up and write this as yh plus yp. Again, maybe some of you have seen this before, certainly usually not done this way for a first order system. But I can open this up, two terms, yh, yp. What is yh? Well, yh is just c to the power of minus integral p dt, and yp is just this big bad looking thing. That is what yp is. I have split it into two, nothing else. And you notice that the yh has a constant, unknown constant, yp does not. Okay. And you notice also that because of the first order equation, presumably you need one constant, one initial condition, that is what we specified, y of t naught equals y naught. But that initial condition is going to go into determining yh, not go into determining yp. Okay. Now, this is called the oh wait, why don't we do that as well? Where does yh come from? If I put q of t equals 0, I get the homogeneous equivalent of this. So, that will presumably be dy by dt plus p of t y equals 0. Okay, we already solved this right at the start. The solution to this is y equals c e to the power of minus integral p dt. Okay, that you notice I have written h, yeah, again sneakily. So, the first term is called the homogeneous part of the solution, because it is the solution of the corresponding homogeneous equation. So, this is the homogeneous part. And this yp is what is called the particular integral, particular solution or particular integral, whatever. Okay. So, for the homogeneous case, you could solve it in closed form, again presumably like this. If p is, you knew what integral p dt was, you can just evaluate it directly, or it is reduced to quadrature. You can evaluate this integral numerically and you will get a solution. And the same thing has happened here, y is equal to yh plus yp. You have yp as being particular solution and yh the homogeneous solution carries through. Okay. If you go back to the initial example that we had, dy by dt plus y equals 2 cos t, the one I used for illustrating the uniqueness business first, or specifying the how do you fully specify the equation. We had this general solution I wrote down was y equals sin t plus cos t plus c e power minus t. This is nothing but yp, this is yh. Okay. So, anytime you have a linear system, this is a linear system, non-homogeneous but linear. Anytime you have a linear system that is non-homogeneous, you can always split it up into two. Take the homogeneous part, which is the right hand side, that q, any term not multiplying y or dy by dt or whatever, drop this fellow off, you will get a homogeneous system. All the terms will contain either a y or a dy by dt or a d square y by dt square, whatever, depending on the order of the equation. And you solve that homogeneous equation, you will get a solution which will contain all the unknown constants that the initial conditions will then provide. Okay. And you can use this solution to generate this solution. That's exactly what we have done without realizing what we are doing. Okay. The fact is that we have used this solution to generate this. I will show you how. Let me start with this. Okay, let me get rid of this. Let me get rid of this. That's where I don't need this. Okay, so the homogeneous solution was this yh plus c e to the power of minus integral p dt. Okay, I can write the yp as same as the yh, but only now I make c a function of x, I call it u of x times e to the power of minus integral p dt. I have taken the homogeneous solution, I have taken the constant in the homogeneous solution, which presumably has to come from the initial conditions. I have taken that constant and made it some unknown function. Okay. Now, if I can solve for the unknown function, then I will get yp. If I get yp, I can add it to yh and I will get my final solution. Okay. So, how do I do that? I take dyp by dx, or dt, not x, is t, sorry, by dt, that is du by dt times e power minus integral p dt plus u minus p e power minus integral p dt. I have taken this derivative minus p of t. I will take yp is just this. So, if I add p of t yp to this, I am going to add u of t p of t e power minus integral p dt to this. I am adding dyp by dt plus p of t yp just to satisfy this. So, this left hand side sum is q of t. Right hand side I have added this, these two will cancel. So, I will get du by dt times e to the power of minus integral p dt is q of t. So, I will get u is integral q of t e to the power of integral p dt dt. I have solved for u, the unknown, and I will put this back in here, and then I will get yp is e power minus integral p dt times integral q e power plus, sorry, e power integral p dt times dt. This is the same as what we had before with the integration factor business. So, I have got the homogeneous solution, I have used the homogeneous solution to get the particular solution. Okay. So, what is the step? The steps were I have a linear non-homogeneous, I took the homogeneous version, presumably solved it, I got yh, then I made yp equals u of t yp is like that. So, yp is this yh with constant equals function of x, that is the u of t, function of t, sorry, not x. And then I put this back into the non-homogeneous equation and then I solve for yp. Okay. This entire scheme is called the method of variation of parameters. Okay, and you can use this for solving any type of linear ODE. It doesn't matter, it doesn't have to be first order. Any linear ODE, you can use this scheme for solving. It's a property of all linear systems. Okay, why is it a property of linear systems? Well, because if you take the left hand side, the general solution y of t is yh plus yp. This is the solution because presumably if you take y of t, put all the derivatives and so on the left hand side, they will all act on this to give you 0 because this is the solution of the homogeneous equation. They will act on this to give you the right hand side like we had for the q of t for any linear system. And so this is a solution that obeys that differential equation. And if the coefficients are all well behaved, which they presumably are, p of t, q of t are all nice functions, they are not strange functions, then you already have a solution. You know solution exists, and Picard's theorem tells you the solution is unique. Okay, so you have a unique solution just by following the sequence of steps. You will see that when you come to second order equations, if you have a second order non-homogeneous equation, you can easily use this to generate a solution for the second order equation. Okay, so it's an important thing, important property of linear systems. So it applies to all systems. We've shown it with the first order system because the algebra is easy to do. I can just do it on this board. The second order system becomes more complex, third order, fourth order, and so on. It becomes quite involved. Okay, good. So that tells us about solving linear first order system. It's fairly straightforward. Everybody has probably seen it. Maybe there is some new way of looking at it here, but content wise there is nothing new. Okay. So what do we do next? The next is, okay, linear systems are fair enough, you can solve them, any arbitrary linear system, any arbitrary coefficients. But what happens when you have a nonlinear, general nonlinear system? Nonlinear IVP. Okay. Now it turns out you can have, under certain special cases, you can cross multiply, you can separate the variables, integrate and reduce it to an integral again. If it's nonlinear, it's possible to do. But those are for very special cases, very special types of ODEs. You can do that by some substitution, by change of variables, whatever. What we're interested in is because we want to go to higher order ODEs, we want to go to second order ODEs, which I mentioned are the bulk of all physical laws. They're all usually second order ODEs. And so in view of that, we will use a general nonlinear system to construct what's called a phase space. Okay, I'll briefly introduce this idea and then we'll take up from here. We'll start off from here in the next session. The idea is as follows. For now, we're going to work only with autonomous systems. So which means dy by dt is just some arbitrary complicated nonlinear function, but only of y. There's no t explicitly there. You can put t, it becomes a little complicated. When we talk about second order systems, I'll tell you what to do when there is t here for the first order case. It turns out there is an interesting analogy between non-autonomous first order systems and second order systems. But the point is that if you have a non-autonomous system like this, then the phase space, what is called the phase space, basically corresponds to the set of all values of y. Okay, y is a number, presumably it's a real number, but the phase space of this system IVP, y of t naught equals y naught, and then t belongs to whatever. The phase space of this consists of all possible values of y, in general, a priori, and it's constructed independent of the initial condition. So, it is only a property of the differential equation, it is not dependent on the initial conditions and on the domain, it does not matter. So, the phase space is a construct that is made only for the differential equation, not for the IVP, although whatever we have been saying so far is okay. I have been barking about IVPs and saying that is the thing we want to solve, but a phase space is constructed only for the differential equation. So, if I give you just this, you should be able to construct this space, you should be able to construct a phase space. Now, I have defined it as a set of all values that y can take, and up front that really is just the real line, because y is just a number, okay, at the end of the day it is a number. So, this is a real line R, there is some origin somewhere, okay, whatever, that is y equals 0, and it is just a single axis, minus infinity to plus infinity, both directions. So, the phase space for a first order system is just a line. Okay, please make sure that you make your peace with it, because this is an idea that will keep coming up repeatedly as we go forward. Okay. So, the geometric picture I kept talking about was in basically trying to see how the solution, remember the solution of the initial value problem, the full solution is presumably something like this. It is some y of t, some curve y of t, which depends on t naught and y naught, the initial conditions that you have specified. The whole point of the graphical picture that we are going to draw is to see how this solution behaves in phase space. Okay, that is what we are going to do. So, I will take this y of t starting at some initial point, and then I will see where it goes on this line. Okay. So, for example, this could be y naught, some value, some positive value, let us say. And so, the solution curve should start here. I am looking at all possible values of y. So, the solution should start here at t naught, and then it can go only this way, or it can go only this way, or it can stay here, because nothing else to do, right. So, if you solve, do all this hard work and solve and get a value like this, at t is slightly greater than t naught, either y is slightly greater than y naught, or y is slightly less than y naught, or y is equal to y naught. There is no other option, right. And so, the solution basically will have to go either like this, or it will have to go like this. Okay. And we will see from the next session that by simply looking at the right hand side of this equation, we can tell which direction it is going to go. Okay. Not only that, we can also say in which direction it is going to end up eventually. Why is that? Well, because if it starts this way, it keeps going this way, and it turns out there is nothing that can push it back. Okay. Which is the property of the line. So, there are now suddenly ideas that come from geometry of a line, that we can use to determine how the solution will go as t goes to infinity, and that is that sort of qualitative idea I was talking about at the start. So, this does not give you a solution curve, that is one piece of information, that is ideal, but if you do not have this, for instance, and for the first order case just illustrative for now, but if you do not have this, you could look at phase space and see how the trajectory evolves, and then say something about long term behavior, short term behavior, things like that. And that is where we will start off in the next session.